Hello viewers, welcome to Master Builders Online Academy. You are welcome, you are welcome, you are welcome. Now, if you are new in this channel, do consider subscribing to our channel and ensure you turn on the post notification bell for more exciting videos. Guys, don't forget our policy. If you are new in this channel, listen to the following policy. Anytime you are set to watch and to learn new concepts from this platform, do not entertain any form of distraction. And also, anytime you are set to watch and to learn new concepts from this platform, guys, ensure you pay maximum attention. Avoid every unnecessary distractions so you can be able to maximize every little content that we drop in this lesson. And finally, if you watch this video for the very first time and you have questions to ask, guys, you have the singular opportunity to replay the video over and over again until you understand it. But if at the end of watching the video over and over again, you still have questions to ask, then guys, don't hesitate to slide to the comment section and make your questions known to us. We will answer your question and give you what you need in details. Now guys, if this is taken, ensure that you like this video, share this video, and make your necessary comments. Now, on the board, we have design of reinforced concrete beam. Design of reinforced concrete beam. This is purely for structural engineers, civil engineers as well. Okay, so if you offer structural design as a course, then this video is for you. We have design of reinforced concrete beam. Generally in analysis, we analyze the loadings, the deflection, and the possible displacement that a structure or a structural member can exhibit. So for every structural member or any structural element, there are possible loadings. And these loadings are what we design against in design of structures. So now in this lesson, we are going to be looking at the design of structural beam. Of course, we know that beam is a structural element or a structural member, and it is a lateral element that resists lateral loads. It is a horizontal element that resists lateral loads. And as such, in analysis, we have different kinds or different types of beams. We have what we call the cantilever beams. We have what we call the simply supported beams. We have what we call the fixed-ended beams, which we equally call the built-in beams. We have what we call the continuous beams, and we have what we call overhanging beams. Then finally, we have what we call propped cantilever. These are the various types of beams that we have in structural analysis, or you call it theory of structures. But in this lesson, we are not looking at the analysis, but we are looking at the design. So in other words, if you will be able to design any structural element perfectly, you must be good in structural analysis. You must know how to analyze the structural loadings so that you will be able to design against those loads. Because there is no design without loads. There is no design without active forces. So if a structure is not carrying any load or is not intended to carry a load, there is no need to design. And that is the reason why every structural member is designed according to the load that is active in the structure or in that particular structural member. So, and of course, we know that in the analysis of building, we have that a load is being transmitted from the roof to the roof beam. Now, from the roof beam to the wall and to the beam, then from the beam being transmitted to the column, and from the column to the foundation. Now, in designing beam in structures, there are three things that you need to put in mind. The definition of beams in design of structure is categorized into three phases. The first aspect of design of beam is that you must consider to know whether a beam, we design a beam first according to cross section. When I mean according to cross section, a beam can either be designed as a rectangular section, as a T section, or as an L section. This is according a rectangular section, a T section, and an L section. According to the position of the beam. And also in structural design, a beam is also defined according to the position of reinforcement. Position of reinforcement. A beam is also defined according to the position of a reinforcement. Now, what do I mean by this? A beam can either be designed as a singly reinforced or it is designed as a doubly reinforced. A beam is either designed as a singly reinforced or as a doubly reinforced. Now, of course, if I have this as a beam, this is the cross section of my beam, and I know that for every structural element, we always look out for the neutral axis, where the center of gravity. So we look out for the neutral axis, where stress is equal to 0. And at the neutral axis, for instance, this is the neutral axis. On top of the neutral axis is where we have the compression zone. And beneath this line is where we have the tension zone. So now, generally for beams, a beam can either be designed at the tension zone or it is designed at both the tension and the what? The compression. So for bottom reinforcement, they are contention reinforcement. And we know that for structural element beam like simply supported beam, we have what we call sagging moment, which exists at the tension zone. So for that, a beam is expected to fail at the tension zone. One of the reasons why we reinforce concrete, as we know, or why we reinforce a beam, is that a concrete is weak in tension, while steel is strong in tension. But the combination of both will give us an effective and active and serviceable structure. So when we have this is the compression zone and this is the tension zone. So generally, a beam is expected to be designed at the tension zone because concrete as a material is weak at the tension zone. So now, any beam that is reinforced only at the tension zone, such beams are called singly reinforced beam. Then while beams that are reinforced both at the tension zone and at the compression zones, they are referred to as doubly reinforced. Now, we'll get to analyze this one after the other. We're going to design beams under simply supported and doubly reinforced. But understand that a beam is said to be designed as singly reinforced only when bottom or tension reinforcement is required. While a beam is said to be designed as doubly reinforced when both tension and compression is required. Now, this is it. So we have compression, we have bottom reinforcement, then bottom and top reinforcement. Then finally, a beam. So we have here a singly reinforced, then doubly reinforced. Then 3, in design of beams, a beam is also defined by what? The support condition. A beam is also defined in structure by support condition. When I mean support condition, like I explained earlier, that we have different types of beam. Now, the way you design a cantilever beam is different from the way you design a simply supported beam. Why? Because a cantilever beam is a hugging moment. So therefore, we design the top of a cantilever. But for a simply supported beam, where you have a sagging moment, we design the bottom of the beam. So you understand that a beam is defined by 3 conditions. So the third is what? By support condition. By support condition. So by support condition, we mean either it is both ends are fixed, one end fixed, supported with a roller, or supported with a pin according to their capacity. Now listen, guys. we haven't ascertained these three ways a beam can be defined in structures. Now, how do I design a rectangular beam? Either as a singly reinforced or as a doubly reinforced. Of course, there are basic things you need to know when it comes to the design of beams. And we are going to go straight into the principles or the procedures of designing a structural member known to be beam. So in designing a structural member such as beam, there are basic principles that you need to know. And these principles you are going to get them very short. But you need to understand that first, a beam is defined according to three things. It is defined according to three conditions. One is the cross section. Two is according to the position of reinforcement, where you have top and bottom, or only bottom, singly or doubly reinforced. Then we have according to support, whether you have a cantilever, fixed end, or you have a simply supported pin or hinge and a roller, or you have continuous beam. Okay, now if this is taken, now let's take a cross section of a beam. Now if this is our beam, if this is the cross section of a beam, now from this end to this end is what we call the overall depth. While from this end to this end is the width of the beam. Now this is the cross section of the beam. Therefore, at the bottom section we have reinforcement. These are the reinforcements. Now all I need to do is to trace the center of this bottom reinforcement. Now from the top surface of the effective depth is the separation between the center of the bottom reinforcement and the top section of the compression zone. Now also we have between the space of the bottom reinforcement or any of the reinforcement at the bottom of the concrete section is what we have as concrete cover. Why this is the concrete diameter? Therefore, if this is the center of the reinforcement, between this end and this center, I have half of the bar size. Now, if this is half of the bar size, then this is my effective depth, this is the overall depth, and this is the width. Now, what is the relationship between the effective depth and the overall depth? Now, from what we have here now, using the knowledge of geometry, what we have that h is equal to the effective depth plus half the diameter of the bar plus concrete cover, which you can rearrange as effective depth plus cover plus half diameter over this. Where D is the effective depth of the beam, C is the concrete cover, which is the separation between the surface of the concrete and the face of the reinforcement beam, of the reinforcement or of the steel bar. Then we have phi or theta as what the bar size, which is the diameter of the bar. Now, if this is taken, now this is only for bottom reinforcement. So when you design for only single reinforcement, this is what you have. Then you can provide some certain reinforcement here so that you will be able to tie these guys. And this is what we call hanger bar if this beam is designed as a singly reinforced. What I have here, they are the hanger bars. But what happens if I now design both a beam as a doubly reinforced? In this case, I'm going to have trace the center of the top reinforcement from this end to this end is what we call D prime. And this D prime is the effective depth of the compression reinforcement. Effective depth of the compression reinforcement. And now we have that this is acting at this center. So in this case, this guy can be equal to C plus half of the bar size. That's what they mean here. So if the depth, the effective depth of the compression reinforcement is equivalent or is equal to the concrete cover plus half of the bar size. This is how you have this. Now, having known that these are the basic properties that I have for For a reinforced concrete beam, the next thing is, what are the procedures for designing a beam as a singly reinforced? I need to know the procedures. Of course, for structural design, there are procedures to design different kinds of structural elements. Now, the way you design a beam is different from the way you design a slab. The way you design a slab is different from the way you design a column. And the way you design a column is different from the way you design a foundation or the footing. So if this is understood, what are the possible procedures, steps that I need to design any structural beam effectively? Now, very quickly, we want to examine the procedures for designing a reinforced concrete beam. Now, like I do always tell you guys, when you know principles, you become a principal. And when you understand boundary conditions, you will not overstep your boundaries. This is very, very important. Now, to design a singly reinforced beam, there are things that you need to know. First is the design of a structural beam starts from design load, which we have as W. And the design load of any structural member using the serviceability limit state is given as 1.4 multiplied by GK plus 1.6 multiplied by QK, where GK is the dead load and QK is the life load or the imposed load. Then, having obtained the design load, the next is the design moment. Design moment. And we have that M is equal to WL squared over 8. This is when you are dealing with a simply supported beam carrying a uniformly distributed load, UDL. Then I can have this as PL over 4. This is when you are designing a simply supported beam carrying a concentrated or a point load. Then you have WL squared over 2. This is when you are designing a cantilever carrying a uniformly distributed load. Then if you have PL, this is when you are designing a cantilever carrying a point load either at the free end or at any distance from the fixed end. Now, if this is taken, once you get your design load, you get design moment. Now, if I obtain the design moment of the structure, what next? The next thing you do is to quickly obtain the moment ratio. What this moment ratio helps you to do, it helps you to identify a beam that is said to be designed as singly or a design as doubly. So what we do here is to find the value of K. Calculate K. And K is the ratio of moment. K is equal to M all over 0. BD squared over F of CU. This value should be less than equal to 0.156. Now, every time you calculate your design moment and divide by the resistance of the concrete, which is the ultimate moment of resistance offered by the concrete, and the value you have is less than what we have on the board, such beams are said to be designed as singly. But when the outcome turns out to be more than this, such beams are said to be designed as doubly reinforced. So a beam is designed as singly reinforced when the ratio of the applied moment or the ultimate moment the design moment to the ultimate moment of resistance of the concrete is greater than or more than 0.156. That is when you design as doubly reinforced. Now, if this is taken, then the next thing that we'll do is, at this point, step number 4, we now calculate what we call the lever arm factor, LA. Now, for the lever arm factor, we have that the lever arm factor is equal to 0.5 plus the square root of 0.25 minus K over 0.9. This is the formula to calculate the lever arm factor, and we are making use of K as the only parameters here. Are you there? And we understand that this K has no unit because it is the ratio of an applied moment to the ultimate moment of resistance in concrete. So as such, there is no unit of measurement. Are we there? So when we substitute the value of K that we have here, we will obtain a lever arm factor. And the lever arm factor have a certain range. We have what we call the lower limit, and equally we have what we call the upper limit. Now listen carefully at this point. When the lever arm calculated is less than the lower limit, you make use of the lower limit. The lever arm calculated is greater than the upper limit, you make use of the upper limit. But if the lever arm factor that you calculate is between the two, is greater than the smallest but less than the biggest, then you make use of the calculated value. Now first we need to understand that 0.775 is less than equal to lever arm less than equal to 0.95. Now this is the lower limit of the lever arm. The least value you can ever have for the lever arm factor is this. While the highest you can ever have for the lever arm factor is this guy. So when you calculate your lever arm factor using this formula and the value you have comes out to be 0.667, being that this value you just calculated is less than the lower limit, you will make use of the lower limit. Then if the value you now calculate using this formula is 0.988, being that the value calculated is more than the standard, then you will make use of 0.95. That is when the calculated is more than the standard. Then when you now obtain the value of lever arm factor from this formula and it falls out to be within these two limits, maybe I have 0.884. Because this value is greater than the lower limit and is less than the upper limit, therefore I will make use of the calculated value. Hope you have, these are the three conditions that controls the lever arm factor, and if you miss it here, everything about the structure is already at a risk. So for a structure to be safe, you must ensure that you put all the factors of safety into consideration. You must ensure that you work within the criteria of BS 8110 design code for a reinforced concrete design. Are we there? So we are working with BS 8110 for reinforced concrete beams. Now, in this case now, just understand that anytime you calculate the lever arm factor, LA, if it's less than this, make use of the lower limit. If it is more than the upper limit, make use of the upper limit. And if it is between the lower limit and the upper limit, then make use of the calculated value. If this is understood, then the next step is to obtain the lever arm itself. Lever arm. Now the lever arm is represented with Z, and this is equal to effective depth multiplied by lever arm factor. So effective depth D multiplied by lever arm factor, which you have already decided from step 4. Then after you have successfully obtained the lever arm factor, the next is to obtain the what? The area of steel for singly reinforcement. And for singly reinforced area of steel, which we also call the bottom reinforcement or the tension reinforcement, AX is given as M over 0.95 FYZ. So this is the formula that you make use of to calculate the area of steel. And it is what you have here that determines the reinforcement that you provide. So first, these are the process. After successfully obtaining the area of steel, the next thing you do is to select steel bar. Now, how do you select a steel bar? You select a steel bar using the table provided by the code of practice. Now, BS 8110 provided a table for area of steel, beam, area of steel concrete, area of slab, area of foundation, area of wall, and all other structural elements. So when you are using the BS table, you must ensure that you are actually using the table that correlates or corresponds to beam. Otherwise, if you pick a value from column when you are designing a beam, therefore you are already putting the life of the users at stake. Then, if this is understood, so you go to the table. From the table, trace an area that is greater than the area calculated. So when you come to the table, pick the area and ensure that the area you will select from the table is greater than what you have when you calculate. But ensure that the difference is not more than 100 meters squared or millimeters squared. The difference. Alright? Then there is also a criteria to check or test run whether the area you provided is adequate or not. So if it is adequate, you will know for high yield steel and for mid steel. Either you check the area provided. When you provide the area, all you need to do, you test run whether the area provided is actually adequate. It should be within the criteria provided by the codes of practice. Now, then you provide an area. Now, the area you provide, when you provide an area, there is also a symbol of notation. Now, the symbol of notation for high yield steel is either you make use of T or you make use of what? This is for high yield steel. Therefore, mid steel is either you make use of R and for mid steel. And for mid steel, you have the strength of steel to be this guy. Alright? Where you have 250 Newton millimeter square. This is when you make use of this. Then when you have from 410 millimeter square and above, then that is when you are dealing with high yield steel. So anytime you are given the strength of steel to be from 410 and above, make use of this symbol when you provide area of reinforcement. Now, another thing you need to know, if for instance I say this is 4Y20, this 4 before the Y is the number of bars. That means I need 4 of it. And while this 20 here stands for the size, the diameter. Are you there? So this stands for the diameter, while this stands for this number. So that means I need 4 bars that are 20 millimeter diameter each. This is why this is the notation, showing that this is what? A high yield steel. So whether I have it as 4Y20 or I have it as 4T20, I have the same thing. So someone that makes use of this and another person that makes use of this, you are saying the same thing, but it is different from when I have 4R20. I am saying that at this point that R, the strength of steel is 250 Newton per millimeter squared. Are you there? So if this is understood, then the next thing you do is, after providing this, then you can begin to check for other necessary things. Now, we have just all these processes we have on the board is for us to be able to cater against bending. Now, when it comes to shear, you need to calculate the shear force, calculate the shear stress, and provide for shear reinforcement, which we are talking about is the links and the stirrups and procedures under bending. So these are the things you need to do to cover up for bending in beam. And we understand that what we do in beams to design beam is that we design against bending, we design against shear, and we design against torsional moment, if any. You need to understand this. One of the reasons or one of the things that we do when we are designing beam is to design against bending. And you cannot design against bending if there is no bending moment. And therefore, there cannot be bending moment if there is no applied load. It is a load that constitutes a moment. And that's what we said earlier, that moment is what? Load or force multiplied by perpendicular distance. So there is no, if there is no load, there is no moment. And if there is no moment, there is no bending reinforcement. So you only design a beam when there is a load that is being transmitted. Now, if this is understood, therefore, what do I need to know more about singly and doubly reinforced? Now, listen carefully. In design, we are actually in design of reinforced concrete beam, we have two major principal elements that are of importance. One of it is the concrete, and the other is the steel. Now, for concrete, the strength of concrete is represented by what? F of Cu, while the strength of steel is represented by what? F of Y. Then, for shear stress, we have F of YV. Alright, so this is strength of shear reinforcement. While this is the strength of steel, then this is the strength of concrete. Now, concrete has its maximum moment of resistance, and steel equally has its own maximum moment of resistance. Now, the ultimate moment of resistance for a steel is given as MR is equal to 0.95 FY/AXC. This is the ultimate moment of resistance of a steel. So, if you are asked as a student to design or calculate for the ultimate moment of resistance, this is the ultimate moment of resistance in steel, or of the steel. Now, for concrete, the ultimate moment of resistance for concrete is given as 0.15 F of Cu BD squared. This is it. So anytime that this is Mu, so this is the ultimate moment of resistance in steel, and this is the ultimate moment of resistance in concrete. Now, get this clear. Now, anytime M maximum bending moment that you calculate from the loading is less than this guy, you design the beam as a singly reinforced. This is another way to test run. Of course, first, we said that when the ratio of the moment to the other is less than 0.156, you design as a singly reinforced. But when it is more than this, you design as a double. Then another way to also know when to design a beam either as a singly or as a doubly is what I'm still teaching you. It's what I'm just teaching you here now. Now listen carefully. This is the ultimate moment of resistance a concrete can offer. Now when you calculate the ultimate moment of resistance that a concrete can offer, and you calculate the ultimate moment that is constituted by the loads or the design moment, which is the moment obtained from the forces acting on the structure. If it is the less than the capacity of the structure itself, then the structure is safe to be designed as singly. So if this guy, Mu, is greater than what? M maximum, then you design as a singly reinforced, because the structure can carry it. We are saying now that the capacity of the structure is higher than the forces that are acting on it. That's what this means. But if M maximum is greater than Mu, that means this structure is no longer safe. So anytime the forces that are acting on a structure has more capacity than the structure itself, then failure is bound to occur. So for us to be able to design against failure, whether now or future failure, then all we need to do is to now provide for bottom and what? Top. Because in this case now, bottom reinforcement is not sufficient enough to make the structure withstand the intended loadings. So for the structure to be able to withstand the intended loadings, you must ensure that the ultimate moment of resistance in concrete is more than the moment constituted by the load. So that's why we provide another reinforcement at the top. So anytime you provide reinforcement at the tension zone and at the compression zone, it shows that the ultimate moment of resistance in concrete is naturally less than the moment constituted by the load, or the moment that is what being induced on the structure via the loadings. So if this is understood, therefore we don't have anything to mock. We don't have anything to kill ourselves for. So first is to understand that for you to design a structure effectively, most especially when it comes to a beam, you must understand when to design. You need to understand when to design as a singly and as a doubly. To design as a singly, ensure that the ultimate moment of resistance in concrete is more than the applied moment or the design moment or the maximum bending moment. While to design as a doubly, the ultimate moment of resistance in concrete is always less than what the applied, the maximum bending or the design moment acting on the structure. If this is understood, then we are good to go. Okay, now we have doubly reinforced beam. Now we have a section From this end to this end, from the top end to the bottom end, we have it as the overall depth. Now from the top end to the center of the bottom reinforcement, we have it as the effective depth of the tension reinforcement. So these ones we have here, they are the tension bars, while these guys are the compression bars. So now, then the indication of this will be 3y, whatever you have, diameter. 3y diameter, then this is also 3y diameter. Now the tensile, the compressor reinforcement is taken as AX prime, while the tension reinforcement is AX. Now for doubly reinforced, like I mentioned earlier, you must understand that MU is equal to 0.156 FCU BD squared. Like we said earlier, this is the maximum bending moment of resistance. This is the maximum moment of resistance that a concrete of any section can induce. So the value of the moment capacity here is dependent on the section, the size of the beam section. So if I have 300 by 150, then I have 450 by 225, I am sure that this guy will give me higher moment of resistance. So the higher the cross section of a beam, the higher the ultimate moment of resistance. Are you there? So the higher the reinforcement, the higher the cross sectional area of the beam, the higher the moment of resistance. So if I want to increase the ultimate moment of resistance of a concrete, then I need to increase the depth and the width. Now, if this is taken, therefore, the resistance of steel, which is 0.95 FYZAXZ. If I also want to increase the area, the moment capacity of the steel, I need to increase the what? The area. And for me to be able to increase the area, I need to increase the bar size. Because what influences the area of any circular object is the diameter. Of course, if I have a steel is like a cylinder. Are we there? Now, if I cut the cross section of a steel, I have a cycle. And to find a cycle, the area of a cycle is pi d squared over 4, which is per diameter. So that means the higher the diameter, the higher the area. Now, the higher the area, the higher the what? The capacity of the steel. So that is to say, if I have 10 mm steel rod and I have 12 mm steel rod of the same length, which one will be more stronger, or which one will offer more resistance? Is the 12 mm, because the higher the diameter or the size of the steel, the higher the capacity and the resistance. Are you there? So the higher the resistance. So if I understand that for me to have a higher strength of steel, I need to increase the bar size. And for me to also increase the capacity or the strength of concrete, I need to increase the cross-sectional area, which is the width and the depth of the concrete beam. And these are what we have as the geometric properties of these materials. Just as we said that there is a relationship between geometric properties of materials and material properties of materials. Sometimes the geometric properties of a material have great influence on the strength of the material. Very, very important. Very, very, very important. The geometric properties of a steel material or a concrete material has great influence on its capacity. So the higher the dimension, the higher the strength. But that does not mean the safer the structure is. No. And that's why we have what we call over-reinforcement, under-reinforcement, and balanced reinforced. So when the reinforcement provided is more than the required, it is called over-reinforcement. And when the reinforcement provided is less than is required, it is called under-reinforcement. And when the reinforcement provided is exactly what is required, that is what we call balanced reinforcement. So a structural engineer can design a structure to be either under-reinforced, over-reinforced, or balanced reinforced. It is better when it is balanced. It is fair when it is over, but it is bad or worse when it is under-reinforced because the life of the people are at stake. But when it is over-reinforced, the engineer runs at loss. This is one of the things because you use more materials than is required. So that is why you need to have a sense of what I need to do to be able to economize some structure. So you need to do it in such a way that you must ensure that there is safety, aesthetics, and what durability. Because the purpose of a structure must be met. And for the purpose of a structure to be met, safety must be guaranteed. Aesthetics, visibility must be guaranteed. And durability must be guaranteed. So if a structure you design as a structural engineer to serve for 100 years, fail at the age of 30, then something is wrong somewhere. Are we there? Something is absolutely wrong. So a structure that is designed must be able to meet up with these three things. One, safety. Two, duration. And three, it should be what? Aesthetics. Meaning it should be one very, very attractive. It should be workable. Now, if this is taken, then now how do I design a doubly reinforced? Now we have looked at singly reinforced. How do I now design a doubly reinforced? For a doubly reinforced, we have compression reinforcement. And for the compression reinforcement, which are the top bars, compression bars, top. The formula to calculate that is A prime is equal to M minus MU all over 0.95 Fy into D minus D prime. This is the formula to calculate the compression bar anytime you identify that a particular structural beam is to be designed as doubly reinforced. So to provide top reinforcement, this is what you do. And you need to understand that anytime you are designing a structure as a doubly reinforced, precisely beam, you design for the top reinforcement first before you design for the bottom reinforcement, because the top reinforcement is needed to provide reinforcement for the bottom. Go ahead and design for the bottom reinforcement first, then you will have it all wrong. So when you are designing a beam as doubly reinforced, the top reinforcement are designed first. So you provide reinforcement for the top first before the bottom, which is the tension. Now, for the tension reinforcement, which also have as tension bars, bottom, we have that AX is equal to MU all over 0.95 FYZ plus the compression bar. So you see, there is no way I will be able to find the tension reinforcement bar first without knowing the compression. Otherwise, I will solve simultaneous equation. Because if you start with this, there is no way you can find the two areas at a time. Now, like I explained before, you know what D is, which is the effective depth of the tension bar, while D prime is the what effective depth of. Now, having gotten these formulas, these models on the board, all we need to do now is to start solving problems using these models. Are we there? We will start solving problems using all of these formulas. So understand that once you identify that a particular beam is to be designed as doubly, first, this is how you design for the tension and the compression bar. And we understand that MU is the ultimate moment of resistance of the concrete, while M is the maximum bending moment induced in the structure by the loadings. So this is also called the design moment, the applied moment, or the maximum bending moment acting on the structure. So if this is taken, I will see you at the other side of the equation. Now, guys, if at this point you are here to subscribe to this YouTube channel, do consider subscribing to our channel and ensure you turn on the post notification bell for more exciting videos. I know you wouldn't want to miss out of the next mind-blowing content. I want to see you in the next session of this lesson. So guys, don't forget to share this lesson, share this video, like this video, and make your necessary comment. Love you guys. See you in the next class.